Good morning, student. Good morning to all. So before I start my class, I will first take the attendance, then I will start. The last class I also mentioned that now onwards I will take first attendance, and basis on the attendance I will tag with your exam. So please inform to others, otherwise those are not present in the classroom, that means the Google Meet, they will face problem, they will be suffered. Just start with the attendance with 9:35, exact time 9:35. This time little bit hurts. Myself little bit hurts. So please make yourself as disciplined. And please inform to other people, your friend. Okay, let's start with your attendance. So be very careful and please respond properly. Roll number 1, Sumon Priya. Roll number 2, roll number 2, Finish. Roll number 3, roll number 4, roll number 5, roll number 6, roll number 7, roll number 8, roll number Dev Shortcut. Roll number 8, roll number 9, 8 also present and 9 also present. Okay, roll number 10, 11, 12, 14, number 12. Roll number 14, roll number 16, roll number 16, 1, 6, roll number 17, roll number 18, 19, 20, 21, 22, 23, 24, 24, 25, 26, 27, 20. Yeah. Roll number 30, 31, 33, 34, 35, 35, 30. Okay, 35 is okay. Sumindo Bhattacharya. 36, 37, 30. Okay. 36, 37 already present. You just, I will just share my screen. Just a second. Just a second. That will be better for you guys. The screen is visible. If I will miss, you please inform. Okay, 36, 37 present, 40, 42, 43, 44, 45, 46. Please check here in the screen. If you are absent, it's showing here. So please inform me quickly. 47, 48, 49, 51, 52, 53, 52, 53, 54, 56, 54, 56, 57, 58, 57 is present, 58 also present. Okay. 53. Good. Okay, now 59, 60, 62, 63, 62, 63, 60, 64, 65, 66, 66, 67, 68, 69, 70, okay, 70, 71, your roll number 71, 72, 73, 73, 74, 75, 75, 77, 78, 79, 80, 80, 82, 83, 84, 85, 88, 90, 92, 93, 93, 94, 95, 95, 90, 96, 97, 98, 99, 100, 100, 101, 102, 103, 104, 104, 105, 106, 105, okay, 107, 108, 109. This is 108. You just go through the scheme, please, very carefully. There is a no modification in further. Be very careful. Anyone left? So your exam code is already here. You can see exam code is 2021012651. I written in the group also. Just a second. I written in the WhatsApp group. So exam time will already started. So please give your exam quickly. Then I will start the class. I will take in the class. Just share the exam code in your chat box also. Your chat box also. So please give your exam first. Then I will start. Exam code is working. Anyone please response? Exam code is working. Anyone please response? Okay. So give the exam. This is the known question. So known answer also. So just give only 5 questions are there. So just give your exam very quickly, very fast. This score, the exam score will your actually reflect time of CA marks. So be very careful about your answer. This basic question. So be very careful time of the exam. This will be reflect with your CA marks. Internal assessment marks also tagging with this exam report. So hopefully you completed your exam. So shall I start? Guys, please respond. Shall I start? Thank you. So I in the last class related with the DSP, I'll discuss with you the various aspect of DSP. So that part is already known. Now I also mentioned in the last class that the one term you already heard, that DTFT, discrete time Fourier transform, when you are in second year and study on signal and system. So basis on that DTFT, we are moving to DFT. So today we will start the DFT part. Before that, again, I just recap this part, different type of signal with the notation. So three major type of signal we already know. That is analog signal, discrete time signal, and digital signal. Analog signal is a continuous in both cases, time and amplitude. Discrete time signal, I already mentioned, discretize the time part. So x-axis is discretized, whether the amplitude is continuous. And another type of signal we also found that the digital signal, whether the both case amplitude and the time part means the x-axis both are the discretized. Now here we discuss the different, again, different types of signal with respect to Fourier transform. So you learn the Fourier transform. So anyone guess? I don't know that you are remember or not in the last class this slide. Anyone guess? Yeah, what type of signal we actually discuss over here? What type of signal here now we discuss? Anyone guess? This signal is associated with the Fourier transform. So anyone guess? Yeah, periodic, non-periodic. I'm not talking about that. What type of signal here we are considering? Yeah, obviously I'm not considering discrete time signal or digital signal or analog signal. Here I am expressing something else. What type of signal here I am expressing? Anyone guess? Anyone? DSP is very easy subject. So just try to understand in easier way, not in the critical way. Anyone guess? Yes, the sine wave is a part. The signal two types, different two type signal here we consider, which associated with the Fourier transform. When we are talking about the Fourier transform, that means two domain of signal we are considering. Now you can guess domain of signal we are considering. Can you guess? Anyone guess? Absolutely, you are right. Your name? Yeah. Shiny. Good. Shiny. And the signal associated with Fourier transform, that means there is a relation of signal we can found. That signal is time domain signal and the frequency domain signal. So two different type of time domain signal we found. Similar with it, we found also two different of frequency domain signal. Let's see. Let's see. So yes, time domain signal we are considering. One is the continuous time domain signal, another is a discrete time domain signal. So this is the continuous time domain signal. This is the function of t. What I am telling here, the x of t we are considering notation. And the time domain signal, obviously this is time domain signal, and the time axis we are considering as a t. And another signal, the discrete. So you already familiar with discrete type signal, whether we are considering n. What is that n? N means this is we call usually time. It's fine. And n is, this is also time, but we add some name, that is time index, isn't it? And our signal is x of n, xn. We are considering. Anyone guess what about these things? What about these things? Sample. And anyone guess the in between two sample there is a gap. That gap is called sampling in frequency. And what about this one? What about this one? This card is called, this is basically your signal frequency. Two different frequency we have found. One is the sampling frequency, another is your signal frequency. You already found, you are already practicing some mathematical problem. You are solving some mathematical problem in your lab also, isn't it? Yes or no? You remember one question is there in the assignment one, probably you plot a sinusoidal signal with some signal frequency with the sampling frequency 1 Hz, and you just plotted 50 sample or 100 samples. You remember that question, guys? Yes. So basis on that, here I am telling that this part is sample, this is sampling frequency, this is time index, this is signal frequency, that's all. What about the next? That is a frequency domain signal. So you just remember, you just notate the notation, whatever I am written, xt, t, xn, n. Now in the frequency domain, again, we are categorized with two different types of signal we found. One is the continuous, another is the discrete. This is the continuous in the above. This is capital X, capital X. We are notated as capital X. Here we are notated small x. Remember, when we are considering time domain, that time we are noted on small x. When we are considering frequency domain, that time we are considering capital X. X omega, and this is in term of discretized. If that continuous signal we discretized, then the notation is basically again capital X, but the under the A, and this is under the omega. Clear? So this is the different type of signal with the notation. Now, why frequency domain is preferred? The main reason, for using frequency domain is to transform linear differential equation into a simple algebraic equation. We can see here, guys, we can see here why we preferred in frequency domain. The first reason, here I mentioned the main reason for the using frequency domain is to transfer the linear differential equation into a simple algebraic equation. The mathematical and hunch about how a circuit works are often simpler in the frequency domain rather compared to the time domain. And frequency domain analysis helps to accelerate and parallelize different development activity we are using in this frequency domain. This is the major key point. We are preferred frequency domain signal. We are preferred to frequency domain signal. This is very important slide. So up to this, hopefully there is a no question because this is definition and another part is your now say see something new. Just give me 1 minute. Now my screen is visible, guys. Fine. Now the second part or third part rather, I will start with some discussion that is the frequency domain and the DFT, then application of DFT, then we are formulated the discrete Fourier transform, and then if we have a permit, we can also discuss the Fourier factor. Now we are moving to the main topic. So be very cautious, be very careful, be very attentive. If you have faced any problem, you just tell me. So before I start my DFT part, I just told you one thing. If you don't have even idea about DTFT, you don't detail understanding of the DFT. So be very careful. Today you just learn this subject. If you have faced problems at this part I'm not understand or something, this part is not clear, don't worry. You just go through any DSP or signal system books and go through the DTFT part. You understand. If you are read very carefully DTFT part. This is very easy thing, you can understand. Then this part will be very easier. So frequency domain and the DFT frequency analysis of the discrete time signal is usually most conveniently performed on digital signal processing for designing general purpose digital computer or specifically design digital hardware. Now the application of the DFT, where we are actually applying, if anyone actually interested to work with this DSP domain project, they require this kind of application are associated. That spectrum analysis is there, that FFT filter band, like a array of band pass filter, data compressions or data compress, we are using DFT. Solving partial differential equation, we also use this DFT. Polynomial multiplication, we require DFT, and multiplication of larger integer, we also use this DFT. And finally, convolution, for convolution purpose, we are also using this DFT. Now, discrete Fourier transform is coming from DTFT. I already told you. So, development in the proceeding section in case of DTFT is concerned with the signal of infinite duration of length. If you know that DTFT, what is the full form of DTFT? Anyone knows? What about the full form of DTFT? Anyone knows? Anyone heard is DTFT? In this semester, in this semester, Otonu sir also taken this part, probably. Either Otonu sir or Molloy sir, I am not remember. So discrete time Fourier transform, when we are performing discrete time Fourier transform, that time the signal is basically, the duration is infinite length. The duration of the signal is infinite length. This is the DTFT. Now, what about the DFT? Now, here we are considering finite duration sequence that extent of length is L. When we are considering DTFT, we are considering infinite length. Now, here we are considering within a finite length duration, we are considering a sequence xn. Now let's see, xn equals to 0, where n lie between the 0 and L. After the Fourier transform, I am not performing guys here the Fourier transform. Just take a reference from DTFT. After the Fourier transform, this is very simple, you know. Also, if we done the Fourier transform of xn equals to 0, we get capital X omega or W equals to, this is omega, equals to summation n 0 to n minus 1. So in the finite length 0 to n minus 1 xn e to the power j omega, whether omega is varied between the 0 and 2 pi. 0 and 2 pi. Anyone guess what about this meaning of xn means? And what about the meaning of e to the power j omega? Anyone guess? What about the difference between xn and e to the power minus j omega? Xn is basically, anyone? This is the magnitude part, and Anyone guess e to the power j omega? Omega is vary from 0 to 2 pi means there is an association with, guys, anyone try? Rotating angle I understand, but what is that? If xn is the magnitude, one equation you have, yeah, phase. This means the phase part. So let us see, we are subdivided. So after Fourier transform, we get this value. Up to this, hopefully there is a no doubt. Now, this capital XW we found already. This is the continuous in frequency domain signal. Are you agree with me? Yes or no? I want the response. Are you agree with me? Yes or no? This is continuous in frequency domain signal, capital X omega. You remember? So two things is there. Capital X omega is there. Another is capital X scale. And similarly, here we can found X T is there. And another is the XN is there. Clear? So now you are agree with me that this is capital X omega is basically continuous in frequency domain signal. And what about the XN? So obviously XN is the discrete time domain signal. Clear? Up to this, any doubt? This response, guys. I want 2, 3 response. I want 2, 3 response. Now, for endpoint DFT, just listen very carefully. We just had this equation. We had this equation, capital X omega equals to summation n equals to 0 to capital N minus 1 xn e to the power j e to the power minus j omega. We have this equation. Now, what I am telling now for endpoint DFT, not a single point. Number of point is n. Number of point DFT. We just simply sample. So we know omega k equals to basically 2 pi k by n. We just sample under 2 pi k by n. Because omega, you know, is varies from 0 to 2 pi. So this part we actually sampled. So for endpoint DFT. And finally, we get that kind of signal. So in place of x omega, so omega, we already mentioned, omega is 2 pi k by n. So this is actually x of 2 pi k by n. We can write down in this way. So you remember capital X omega signal is basically, this is the signal we found, and capital XK signal, the same signal, but it's sampled. Isn't it? Is that clear, guys? Yes or no? Tell me. We just sample it. And that sample signal, we can say this is frequency domain discrete time signal, which is here I am written that W. In place of W, we write down capital XK. And in place of xn e to the power minus j omega, in place of omega, we write down here 2 pi kn by capital N. Just this part will actually put over here. Clear? We are done Fourier transform, but in endpoint DFT, in term of endpoint DFT, we just sample it. And the interesting part, where n equals to 0 to 1, 2, 3 up to n minus 1. Now, using endpoint DFT, we found the revised or modified formula, that is capital Xk equals to summation n equals to 0 to n minus 1 xn e to the power minus j 2 pi kn by capital N, whether small n varies from 0 to n minus 1. This is equation 1, and we can found xn is the time domain sample and capital Xk is the frequency domain sample. Now, as per the definition of the endpoint DFT, the relation in equation 1 means the previous for equation. The formula of transforming a sequence xn of L less than greater than less than, this varies. L to n into a sequence of frequency sample capital Xk of length n, and this is the definition of the discrete Fourier transform. We are not at all more interested at the definition. The interested we are about the formula. So this is the formula of DFT capital Xk equals to summation n equals to 0 to capital N minus 1 xn e to the power j 2 pi kn in by n. This is the formula of DFT, from where this will basically come, came from DTFT. This came from DTFT. In DTFT, what we are doing in infinite duration signal, or we are done infinite duration of signal. For DFT, we have a finite length. So basis on that we get this formula. Now let's see. Now we are trying to find out the recover sequence. Recover sequence means we are now finding the DFT. If we are doing the reverse process, so you know, so if you have a car, if car are moving in forward, sometimes they require the reverse also. So similarly, we have a formula. This is for the DFT. So we are moving to the reverse DFT, or we can say inverse discrete Fourier transform, or IDFT formula. What is that? This is very simple. Just 1-2 things changes over here. So what about the DFT formula? Capital Xk. Please tell me, anyone, what is the formula of DFT? Capital Xk equals to, anyone? N equals to 0 to n minus 1, then good. E to the power minus j 2 pi k into n by capital N. This is the formula of DFT. Yes or no, guys? Other people, please respond. Please respond. Yes. Now the DTFT formula. So this signal is frequency domain signal. This is basically time domain signal. So that means when we are reverse part is coming, that means this is again the time domain signal. This is the frequency domain signal. In case of DTFT, in case of IDFT, inverse discrete Fourier transform, that minus symbol is vanished. There is a no minus symbol. This is plus, and one part is added, that 1 by n we are actually added before written the summation symbol. This is the inverse discrete Fourier transform. You just read 3 times and write 5 times. Ever you forget, ever you are not forget this value. Ever you are not forget this value, this formula. So this is very easy formula. This is very known formula. From where to come we make this formula, I already discussed. So this is the formula of DFT and IDFT. So here I just accumulate the DFT and the IDFT formula. This is, we call usually, this is the formula of endpoint DFT. Later on we understand why we call this is endpoint DFT. Why we call this is endpoint DFT. So this n having some value. So later on in the next class we discuss about this endpoint DFT in detail, but today we are discussing the basic formula of DFT and IDFT. DFT, inverse DFT. So this is equation 1, this is equation 2. So up to this I am not today discuss about the twiddle factor part. So up to this, so now this is 1019 also. So hopefully you are already give your exam in IMCRP. So thank you for attending. So I again request you guys, please go through the DTFT. Please go through the DTFT. That DTFT are present any signal system or DSP books is present. Okay. So thank you for attending the class.